In the following video, we'll go over how to solve for the amount of time necessary for a compound interest problem. Now first, recall the compound interest formula, which says that the future value A is equal to the present value P times 1 plus I, where I is the interest rate per period, raised to the n, where n is the number of compounding periods. Now another way to think about this is that the future value is equal to the present value times 1 plus R over M, where R is the annual interest rate and M is the number of times compounded in 1 year, so therefore R over M is the same thing as I, because you're taking the annual interest rate divided by how many times you compounded in 1 year. All of that raised to the M times T, where again M is the number of times compounded in 1 year, T is the time in terms of years. So when you multiply M times T, that gives you N, which is the number of times the interest will be compounded. Now for this first example, you're to find how long it will take $4,000 to grow to $9,000 if it is invested at 7% compounded monthly. Now to solve this, you got to also recall a couple properties of logarithms. First, if a and b are values greater than 0, where a equals to b, then the natural log of a is equal to the natural log of b, so that's the first property. And then the second property is the power property for logarithms, that if you have the natural log of a to the r, you could move down the exponent to the front of the logarithm and it'll be r times the natural log of a. So as is the case with most of these compound interest problems, you first plug in what you know into the formula. So we know our present value is 4,000, our future value would be 9,000, the interest rate R, the annual interest rate is 0.07, M is equal to 12. Now if we wanted to use the other formula with the I, we could just plug it in and get that I is equal to R over M, which is the 0.07 over 12. So plugging those into the compound interest formula, we get that 9,000 is equal to 4,000 times the 1 plus 0.07 over 12, all of that raised to the 12 times t, where again t is the number of years. And 12t would therefore be the number of times it's compounded to get from 4,000 to 9,000. So we need to solve for t. So the first thing I'd do is to figure out what's inside the parentheses. So we'd have 9,000 equals to 4,000 times, now what's inside the parentheses is 1.0058333 with the 3's going on forever. Now one thing is, don't round in the middle steps. You got to make sure to carry all the decimal places. Now the next thing to do to solve this exponential equation, and again this is an exponential equation because the variable is in the exponent, we got to get the exponential, which is the 1.005833 to the 12t by itself. So I divide both sides by 4,000, and so we'd have 9,000 divided by 4,000, which simplifies down to 9/4. And so that would be 2.25 equals to that 1.005833 raised to the 12t. Now that we have the exponential by itself, we use that first property of logarithms that I mentioned, which if these two things are equal to each other and they're both non-negative, then the natural log of those two things are also equal to each other. And then we'd use a power property of logarithms, so we could bring down that 12t to the front of the logarithm. Now remember, the natural log of 2.25, that's just a number. You plug it into your calculator, you get a number. Same thing as the natural log of 1.005833, going on forever, is also just a number. So we really have 12 times t times another number equals to another number. So we just have a pretty basic linear equation. So I would next divide both sides by that 12 natural log of 1.005833. So if we plug in the natural log of 2.25 divided by 12 times the natural log of 1.005833, again the 3's going on forever, you get approximately 11.61847. So let's say, rounding it to one decimal place, that this says it will take about 11.6 years. Now for the last example, let's find the time it would take for the general level of prices in the economy to double at the average annual inflation rate of 4%. Now in this case, we don't seem to have an initial amount, but you'll see that it won't matter what the initial amount is. So one thing we do know is that R, the annual interest rate, is 0.04, our inflation rate in this case, and M is 1 because we're told that this is the annual inflation rate. So this actually tells us that R and I are the same thing because it is an annual interest rate. Now let's let P be the general level prices, and we're trying to find when for it to double, so we'll let A equals to 2 times P. And you're going to see it doesn't actually matter what the actual level price is, that the amount of time it takes to double will be the same no matter what P is. So let's plug this all into the compound interest formula. So we'd have 2 times P equals to P times 1 plus 0.04 raised to the, well, it would be M times T, but in this case, since M is 1, it's just 1 times T, so it would just be to the Tth power. So that would be 2P equals to P times 1.04 raised to the T. Now, next thing I would do is divide both sides by P, and if you notice, what happens then is the P's cancel, so you just get 2 equals to 1.04 raised to the T. So that's why, again, I was saying it didn't matter what the actual price level was. The amount of time it would take to double would be the same no matter what. So again, now we have the exponential by itself, so we take if those two things are equal to each other, then the natural log of those two things are equal to each other. And then using that property of logarithms, I could bring down the T to the front of the logarithm. Now once again, natural log of 2, natural log of 1.04, those are just constants, so we divide both sides by the natural log of 1.04. So you get that when you plug it into your calculator that T is equal to 17.729 dot dot dot. So if we round this, let's say, to 2 decimal places, it would take about 17.67 years.